Herein we'll give a brief introduction to the carboxylic acid. We'll talk about the nomenclature. Most of this you'll be familiar with, and then we'll give an idea of the structure and properties. So for example, acidity, is based on the stability of the conjugate base. More obvious when we're talking about carboxylic acids. Boiling points and melting points can be determined by the ability of these carboxylic acid to go through a specific type of hydrogen bonding. Solubility, of course, is because of the OH that's present. So you can see that the lower molecular weight acids will be soluble in water. Preparation we've come across before. We may expand upon that. And in spectroscopy, there are specific patterns or specific bands or patterns in bands that we'll see in the infrared. And we can also look at the deshielding on the acidic proton in the proton NMR. Acids are of course abundant in nature, and of course we already come across them in some pharmaceuticals. So for example, aspirin, which is acetylsalicylic acid, is well known, and p-aminosalicylic acid, which is frontline drug against tuberculosis, is also something that you're familiar with. As far as the derivatives are concerned, you can see that if we have, instead of the OH, we displace it with the chloride, then we'll have acid chloride. If we have, instead of the OH, then we have an acetate. Then if we have an anhydride, you can see acyl phosphates. These are very important in nature, very ubiquitous in nature. And of course, also the esters. You can see thioesters and amides. For some reason, nitriles are also carboxylic acid derivatives. You should be familiar with these. Nomenclature is not difficult. What you got to realize is that the species is a carbonyl, and so it is dominated by the numbering scheme that you get from the carbonyl. So for example here, you can see we start off with carbon 1, 2, 3, 4. So this is butanoic acid. Here you can see that the longest chain is 1, 2, 3, 4, 5. And you can see that on 5 you got a hydroxy, and of course you have some dimethyl, and you just go about it alphabetically. For ring compounds, of course, you can just go ahead and tell the reader that you have this alkyl group on the carboxylic acid. Some common names, you should have in mind. You have like butyric acid, and you've already come across benzoic acid. The dicarboxylic acids are terribly important, so a lot of these you've already come across in your biochemistries that you've done in the past. And of course, the ones that I want you to keep in mind, or the one that I want you to remind yourself of, is the malonic acid, because the malonic acid synthesis and its congeners, the cetoacetic ester synthesis, will be important to us moving forward. If you look at the structure of the acid, you can see that the proton, if you look at the electrostatics, you can see that where the proton lies is quite blue. That means it's quite acidic. You look at it, typical sp2 carbon, so it's planar. Of course, you realize that the bonds are quite polar. This is interesting because this is quite unique amongst carboxylic acids. You can see that the acids themselves exist as a diamond. So of course, when you look at the boiling points, it's much higher than, say, for example, an alcoholic conjugate. The same would be reflected in the melting point. As far as acid strengths are concerned, I would like to remind yourself that the lower the pKa, the more powerful the acid. You can think about this acetic acid, for example, in water, gets deprotonated, of course, to give you the conjugate base, yes, and the protonated species, yeah, the proton. The more stable this conjugate base, of course, and the more acidic the species is. You compare that to what happens when you deprotonate an alcohol, you get an alkoxide, yeah. The alkoxide, the lone pair, or the negative charge, is sitting only on that oxygen. However, with the acid, you can see that there is a number of resonance structures associated with it, 2 to be exact. Here we are showing you the hybrid. The more stable the conjugate base, as we stated before, the stronger the acid, i.e. more resonance or presence of resonance, yet greater stability. The Henderson-Hasselbalch equation you've come across before, and it relates the amount of acids and its conjugate base to the pK and pH values. First, I can never remember the equation, but I can determine it from first principle. If I deprotonate, yeah, to give my conjugate base, you should realize by now that the acid constant, i.e. this dissociation constant, is the protons, yeah, times the conjugate base, divided by the starting material, because remember the water is a constant. So this is the acid constant, or acid dissociation constant. If we log this fellow, or give it a minus log, then you can see that pKa is the pH plus the log of HA over A minus. And of course, you can take this fellow and put it over this side, and take this one, put it over that side, and that will give you, yeah, pH equals to pKa plus the log of A minus over HA. Electron withdrawing substituents on the carboxylic acid will stabilize the conjugate base. And so, for example, if you look at this trichloroacetic acid, yeah, the pKa is quite low, so we have a very strong acid compared to, say, this standard acetic acid with a pKa of 4.8. This is due to the electron withdrawing effects of those chlorides on the alpha carbon. We know it's induction because if we look closely on the halogenation of the butanoic acid, you can see that 2-butanoic acid, which has the chlorine on the alpha carbon, is much stronger acid than 3-chlorobutanoic acid, which is much stronger than 4, meaning that, yeah, as we move further away from the carboxylic center, then the Ka is greater, i.e. the stabilization due to this electron withdrawing substituents is less. If you look at benzoic acids again, yeah, remind yourself that the benzoic acid, because you have the ring, then of course this guy here is a little bit more stabilized, and so you can see benzoic acid has a pK of 4.2. If we think about that as the standard, right, then you can see that activating groups, well, this is the basis point, activating groups will decrease the acidity, i.e. you can see an increase in the pKa. On the other hand, yeah, you have deactivating groups, electron withdrawing groups, and you can see there is an increase in acidity, i.e. a decrease in the pKa. Note that nitro is a very powerful electron withdrawing group because it is pulling electrons via resonance. The question is, what position do you think the electron withdrawing group should be placed to optimize their effects? We can ask a question like this, for example: which of the following substitute benzoic acid is the strongest? And that will give you an answer. We can discuss this in class. Let's pause right here so you can work it out and make your notes, and we'll talk about it then. So to summarize, we should realize that if we have withdrawing groups, then of course we're going to stabilize the conjugate base, i.e. weaken the base, i.e. the more stable the conjugate base, the stronger the acid. On the other hand, electron donating group, then we destabilize the conjugate base, i.e. less stable conjugate base, weaker acid. There are a number of features in the spectroscopy that one wants to remind ourselves of. And we'll also look at the derivatives as well. But the main feature of the carboxylic acids that I want you to remind yourself of is the infrared having two significant peaks: the OH, which is hydrogen bonding, and the C double bond O, which, as you know, both of these bonds are polar, so the intensity will be quite strong. And in the proton NMR, you would have a rather de-shielded, how more de-shielded than you get than an acidic proton of the acid. And of course, in the carbon, you'd have a typical carbon ion. Carboxylic acid derivatives will review amides and nitriles. So, as stated, the infrared, the carbonyl group, of course, absorbs at around 1700, and of course the OH really broad at 2500. The proton, you can see, is deep, at 10 to 12 ppm. So here we have an acid, and you can see immediately the broad OH that is present, and it is usually very strong, and then of course, very noticeable, and then of course you can see the C double bond O stretch that we have here appearing in the 1700s. Less significantly is the CO stretch. In this spectra of propanoic acid, what stands out is, of course, the de-shielded proton at 10 to 12 ppm. Remind yourself that this is the area of aromaticity, and if you had an aldehydic species, then of course it would be in this area. So this is very deep, very de-shielded. In the carbon, of course, we can see the carbonyl. There are values that are used, values of carbonyls are used to predict which carboxylic acid derivatives you have, and we can discuss this at a later date. So here we have infrared spectra of two different amides, right? And we're trying to figure out which one is the primary and secondary, right? You can see, for example, that we do know we have some sort of carbonyl, and then we have some NH. But if you look closely at the NH here, then you can see we have a single bond, which tells you that you have a secondary. And here, we have this doublet, which tells you that we have a primary, i.e. we have an NH2 present. The nitrile is quite special because they're triplet bonded species, and so that would appear way above 2000. In fact, it appears around 2200. It's very sharp and it's medium because this bond is not very polar. You contrast that to the carbonyl, which appears lower because the bond order is much less. And it's also, the carbonyl also appears stronger because it is more polar, i.e. oxygen is more electronegative than nitrogen. And we needed to work on this one. We can discuss it in class. So we have a compound molecular formula C4H8O2. Of course, we're doing acid chemistry, so you'd assume that this is an acid. So you can see the carbonyl. The carbonyl here and the OH here. And what we need to do, there's also a broad signet here. You can't really see it that well, but that will tell you that you do have an acid. And then you have some multiplet here and the doublet there. So work on that, and we can go over this in class. I will pause right here. I will accept you to pause and review this and do the work, and then we'll talk about it in class. Here we'll talk about the preparation of carboxylic acids. And if you note, quite a few of these preparations are going to be work that you've done in the past, and some of it will be quite novel. So let's go through them as seen on this page. If we have a primary alcohol, the organic 1, we can oxidize it using chromium 6 or manganese 7 to the acid. So for example, we have some sort of benzol, and we've oxidized it up to the acid. We could have used a normal alkyl or primary alcohol as well. If we have benzyl arenes, as long as we have on that benzyl carbon a proton, then oxidation will take place, as we've seen previously, and we'll end up with the benzoic acid. If you have not seen Grignards before, Grignards are quite easily made. If you got some sort of alkyl or aryl bromide, then you can react it under anaerobic conditions with magnesium turnings to give you a Grignard. This is a carbon anionic species. This carbon here is anionic, and of course this carbon dioxide is going to then act as your electrophile. You quench out and you end up with your acid. We can also hydrolyze nitriles under both basic and acidic conditions to give us the acid. This is something that you've done in the past under oxidative conditions. When you perform the cleavage, you should end up also with acids, with the alkenes and alkynes. Have a think, because you've done this already. So as long as you have some sort of alpha hydrogen, then the oxidation will take place. You can see that, even though I'm working with KMnO4, the reaction will not stop at the aldehydic stage. For it to stop at the aldehydic stage with a primary alcohol, you'd have to treat it with something like PCC, which is a milder oxidant. if we use KMnO4, we're going to drive all the way through to that, from the aldehyde through to the acid. So this will be our final product. The same thing here. Yeah, I'm using the chromium 6 and it does the same thing. Note, you went from chromium 6 to chromium 3. You went from manganese 7 to manganese 4. So we have oxidized our substrate and at the same time reduced manganese from 7 to 4. Of course, we learned about the oxidation of the benzyl carbon. Here is our Grignard reaction. Note, the Grignard, all it is indicating, yeah, and we'll talk about this at some later time, is with this compound here is product of this aryl bromides with magnesium. If you look carefully, one representation of this compound would be, of course, the anion being at that para carbon, the carbon para to the methyl, i.e. the carbon where the bromine once was. And then you can think of the MgBr as your counter cation, because this total species here is a plus charge. We can then react it with carbon dioxide and then quench to give us our acid. So a typical way we could make an acid, yeah, is you can see here, for example, we're using some sort of benzylic species. We're going to brominate it and then we convert it to Grignard, and then of course now we add the carbon dioxide quench. It is a coupling reaction because, as you can see, we've added an extra carbon to your substrate. The mechanism, of course, looks like this. You use, yeah, think about the aryl group or the alkyl group or the benzyl group, yeah, the anion will attack, yeah, the electrophilic center of the carbon dioxide. You're going to be using this resonance structure of the carbon dioxide. Realize it is a carbonyl, so it is an electrophilic attack on your carbon. It's a nucleophilic attack on your carbonyl. So this is the electrophilic center here, not carbon. So the attack occurs, you went from an sp carbon to now a carbon which is sp2. And then you quench, i.e. you stop the reaction, right, or neutralize the reaction with the acid, with the mineral acid, to give you your desired product. Herein you can see a bimolecular event where you have an alkyl halide with the cyanide and you generate the nitrile. Again, this is a coupling reaction because you just added a carbon to your substrate. You added a carbon to your substrates. The nitriles are very useful synthetically because we can reduce the nitrile to an amine, a primary amine. But in the context of this chapter, we can go ahead and treat it, hydrolyze it with an acid or a base to give us the carboxylic acid. This is something that we've done in the past because here you can see that we've cleaved under oxidative conditions, and that will generate our acid. Note here, yeah, we have the alkene on one carbon flanked by two R groups, and so we end up with a ketone. And here we still have this proton present, and so we end up with our acid. Remind yourself and ask yourself, what would happen if I done this reduction using dimethyl sulfide? So ozone followed by dimethyl sulfide. yeah, which are reductive conditions. So these are the sort of ideas that should be in your head, or the reagents that should be in your head. These are the reagents that you should have in your memory banks. These are the reagents that will help you to form carboxylic acids and their derivatives. So a question like this should be quite obvious to you. You can see that we have this ethyl chloride and then we green yellow carbon dioxide quench. This of course is coupling reaction. We've added one carbon. Have a think about that and we'll talk about it in class. So as far as reactions of carboxylic acids are concerned, the only area that we'll look at is, at the present moment, is we'll look at the reduction of these acids. These areas here, yeah, we'll leave until another time. Reduction, of course, yeah, can be carried out using lithium aluminum hydride. It's a very powerful reducing agent, lithium aluminum hydride. So we lithium aluminum hydride quench, and what we end up with is a primary alcohol. A primary alcohol we could use a milder Borwein, yes, and it's much more selective compared to lithium aluminum hydride, because unlike lithium aluminum hydride, which reduces everything on the planet, yeah, here the Borwein, given the option between an acid and a ketone, it is sterile to the ketone, and so it only reduces the acid portion of this molecule. Separation of benzoic acids from, say, cyclohexanol or other organics is a concept that you've done in the laboratories, or if not, you're going to do it in the lab. And simply put, if you have an acid mixed with another organic compound, treat the acid with a base, and the acid itself will now become a water-soluble salt, which you can then separate in an aqueous solution. You can take that aqueous solution and then treat it to a mineral acid, and this will regenerate your carboxylic acid, which you can then extract using an organic solvent such as dichloromethane. So we can easily ask a question like this: which of the following pairs cannot be separated by the extraction based on their acid-base properties? And first of all, you can see that here, for example, yeah, we have an ether and an alcohol. And of course we can basify this lot and separate it from here. Yeah, of course there's a difference in the pKa and so on. And what we want to do is therefore find out which of these guys here we cannot separate out. And then we can discuss this, yeah, in our session. This is the end of the chapter, and this will also be included in your test on Thursday.